Sorry, I'm late. So, any questions on anything for the homework or anything? No, right. So, anyway, last time I went through these ones work. So it's like three peak capacity things. One fatigue, Einstein, and 5. And so basically the Dulong fatigue, if you look at it, is just like a spring. See, I mean, you have a crystal, and it's got going off in space, you know. So the Dulong fatigue kind of looks at a pair of these and says it's a spring. And so you have the force is A times X, and the energies KX squared over 2. Then you do a balance, and then you kind of end up with the CP by R is 3. Einstein, you say that it's a guitar string, so you also are just looking at the one, and you say it has different modes. Here's the 0 mode and another to infinity mode. So the vibrations, like a guitar string, would have different modes of vibration. Then you get that answer for the high temperature. You get CP by R is 3, and then at lower temperature, you get the Einstein equation, which is squared Einstein temperature, which is the Einstein frequency over K, and then exponential of Einstein temperature over T, and 1 over, and then exponential Einstein temperature over T minus 1 squared. Like this thing, anyway, and then there's a proof factor to this, but basically, I guess R, CP by R is going to give you something like that. So this kind of expression gives you the behavior. It's actually, this is all for CV. So it shows you the behavior of CV. It should be CV2. And so versus T, the petite's a constant, so it's like 3R. And then Einstein's going to plateau out there and come down like that. But the data points are kind of a little bit off from that, basically close. So Einstein looked pretty good. The Debye model is more of a 3D model. So it's looking at, it'll be an integral over 3D. So it's going to be a 3D model. And it also involves like coupling, because it's 3D, it involves coupling of the coupling of the vibrations between the atoms. So end up that you'll have like, well, all right, so the Debye model is more sophisticated. Like it involves like phonons. But it's more sophisticated than the Einstein model. Right? So you have to understand what a phonon is before you can do the calculation for this. But in the end, it's a 3D model that includes collective, or like collective motion. So it isn't two things. It more or less is like, and you can think of it as like 3 things. 2 guitar strings connecting 3 things. So it'll be like I minus 1 and I plus 1 atoms. And when a vibration comes, it moves this atom. These atoms are out of phase. So there's a phase lag between the motion of this atom and that atom. Right, so phase lag comes into play in the Debye model. The first part of the Debye model, though, is just an integral similar to the Einstein model, but you do it in 3D, and that gives you the Debye equation, which is kind of like more elaborate than the Einstein equation. So it's this thing down here. So CV, I guess not more elaborate, but it's an integral. So the argument, so this is just a function that gives a number, right? So it doesn't matter what the x is. The limits of x is 0 to the Debye temperature by T. The Debye temperature is similar to the Einstein temperature. It's a frequency h nu over k type thing, but the frequency is a Debye frequency. Okay, so it kind of looks similar to the Einstein. It's got like x4 here and t to the cube here instead of t squared. Right. So, and then there's a factor of 9. So the function's a little bit different than the Einstein function. Anyway, so and this integral is called the Debye's second Debye integral. So the first Debye integral, this is a second Debye integral, and there's a third Debye integral. It's also with the this is like a math function. They can, I mean, some computer programs have that already programmed, like a second Debye integral to get the heat capacity. Anyway, so the way that works is that and if you look at the comparison with data, up here is a lot of that. So the Debye matches is a dashed line and the Einstein is a solid line. I mean, they look comparable, but basically the difference at this end. Like it matches the data better. Then there's a difference at the low end in that this follows t cubed at that end, and the Einstein follows like an exponential. So they aren't the same functionality when you get close to absolute zero, which becomes important for superconductors and things like the homework. Right? So anyway, so that's one aspect of the Debye model. So I went through the Einstein on whenever Thursday, I guess. Let me hide this thing. It doesn't want to hide. There. Let's see. I think the Zoom, well, the whole computer is going pretty slow here. Let me go back here. Go through the Einstein. So that's the Einstein. I mean, so this lead term in the Debye, it's T by theta D, and in the Einstein is theta E over T squared. I mean, in the Debye, it's T by theta D cubed, and that ends up being the low temperature dependence. The other term drops out, the low temperature. And in the Einstein, somehow it ends up being an exponential at low temperature. I'm not sure how that exactly works out, but I guess this is so when the temperature is low, this term gets large, then you can forget about the 1, that cancels, and you get 1 over, so this cancels with the squared. So you have 1 over, so e to the minus theta e over t. And I guess that's a stronger dependence than this 1 over dependence at low temperature. So it ends up just being an exponential decay at low temperature for the Einstein, which matches, like in the homework from last week, it matches pretty well when you have a case like in this aluminum intermediate phase that not intermediate. Anyway, this aluminum compound that where the aluminum atoms are free. So if you have a free atom, then it does vibrate as if it was like a single, like a free atom with no influence from the other atoms. So Debye accounts for the influence of the other atoms by doing a 3D integral to get the equation. And then also for the dispersion relation, which I'll go through, it's more discrete how it's involves the collateral interactions between the atoms. So anyway, So this stuff's kind of complicated and kind of dry, but basically you'll see it like everyone's going to be using this when they get to the complicated part of what they're talking about. Then it's all this kind of thing like the phonons and the bi-integral. The whole approach here sets up a framework for how people deal with complicated material systems, crystalline systems mostly, but also the same approach is borrowed when you talk about dynamics. So it's kind of a funny thing, like this math was going around. So like if you talk about polymer flow, which aren't crystals in a liquid state, and you talk about what's the dynamics of a polymer in a liquid state, use a thing called a Rouse model, which is the Debye model adapted for polymers. Okay, so it's kind of like all the math of the Debye model is just taken and then dumped into a polymer chain, how a polymer chain moves through a fluid, like the relaxations of a polymer chain. So basically, it's basically this math is kind of borrowed for everything, a lot of other things. So it's kind of a framework that people use for different things, and they don't acknowledge it. They'll just say, "Oh, we invented this." It's kind of a funny thing. Like you have to know that this exists to know kind of where things are coming from, But also at the time, like there were a lot of, like at the turn of the century, like 1800s and 1900s, there was a lot of innovations of understanding of like quantum theory was developed, and like basically a lot of understanding of materials on an atomic scale was developed then. So this is one of the contributions to that, like one of the major contributions, So anyway, so if you have, so I think last time I mentioned this, that you have atoms, so black things are atoms, and then you have a phonon coming in, which is going to shake the atoms. Right, so there's two ways to shake the atoms. You can do it in optical. If you have like NaCl, you have some Cl's in the, you have Na in a phase center cubic, and then some Cl's in another phase center cubic superimposed on it. Then if you say you put a light wave in, so you put an electric field on it, and these are like minus, these are plus. So this guy is going up and that guy is going down. Right. So there is a motion of it. So a phonon exists, but it's not a, versus if you put a actual force on it. It's like a phonon would be like acoustic phonon would be an actual force, but on materials, you say like, if I squish it or I vibrate it like that, then I'm going to push these atoms like that way, and then the next atoms, so there'll be a phase lag between the atoms, right? So this wave of motion, like a compression of a density and then a decompression, that wave is going to move down, right? So that's a longitudinal. That's a longitudinal wave, right? Longitudinal acoustic wave. So that would be a compressive wave, like so you set off an explosion, it compresses the material, and that wave of compression progresses through the material, like because it's, say the atoms are all put together by springs, so they compress and then decompress. And so it's going to move through it. So that's a longitudinal acoustic vibration of material. You can also have a transverse acoustic wave going through material too. Right, so that's kind of like one way that phonons can move through a material. Those very depends. Okay. So that's longitudinal acoustic wave, and you can also have a transverse acoustic wave. Right, so transverse acoustic wave would be like you have a rope and you just shake it, right? So you shake the atomic plane and the atoms move up and down like that, right? But it doesn't matter if they're Na plus or Cl minus, they move like a wave, right? Like the things on the atoms here are moving by a transverse acoustic wave, because they're all black dots. If they were black and red,
they might move in different directions due to being stimulated by light. Right, so when they move in different directions, that's called an optical wave. Because basically electric field, so the light is going to be an electric field, and then a magnetic field 90 degrees, like coming out of the board. So the magnetic field and the electric field are offset by, so that where there's a peak of electric field, the magnetic field is zero. And where there's a zero of electric field, the magnetic field is maximum. But the magnetic field is coming out of the board. And so they just oscillate, kind of like between potential and kinetic energy, just oscillating electric and magnetic energy through space, and it progresses. So anyway, if you have plus and minus charges, and this thing comes on, which is light, then it's going to make the chlorines will go up and the sodiums will go down, and you have this opposite shaking going on, right? So it isn't like an acoustic wave. It has features that are different. For instance, if you go to large size, so say you went to the absolute largest size, like your sample size, like a meter, then the acoustic wave would make the object move, right? It would actually, that would be a bulk motion of it. And as you get to smaller size, then you get to the bulk modulus, you get to very small sizes, you get the atomic cohesive density of the atoms, right? So over the size scales, the behavior of the material is going to change. Like at large size scale, the thing actually moves across the table. Then you get to the modulus, and finally get to this cohesive density of the thing. And so it's the size scale going to interfere with like how these waves behave. Interaction between this kind of force that you put on the material and then the material structure, right? So that's kind of where this phonon thing comes in. So, and then light also kind of does this kind of moving things around if they're charged, and you get these optical, and depending on which crystal plane you're looking at. So this is going to have like a 100 plane, like these planes, 111 that goes kind of diagonally, and a 110 that goes a different way diagonally, right? So all those planes are going to behave differently. They're going to absorb phonons or kind of mechanical energy differently, right? So and optical energy that translates into a phonon. Right, so it's a complicated thing. So you're going to see, you want to know like the distribution. So you dump some energy into the material. You want to know like what's the distribution of that energy when it goes into the material, right? So that's the density of state. So this is for cuprous chloride. So it's like NaCl. So it has optical waves. So it's got longitudinal optical waves, transverse optical waves. So transverse is like a normal wave. Longitudinal is a sound wave, like a compressive kind of wave. Then it's also got acoustic waves that are at a lower energy, lower frequencies. H nu is energy, so lower energy. Right. So this is called the density of state. So if you dump some energy into it, it's going to distribute that energy into these peaks. Right. So, or you could think about this as if I shoot say light into it, then I would only be measuring the optical components of the vibrations. Then I would get, this would be the optical spectrum, like I'm doing a Raman spectrum or a Brilliant spectrum or an IR spectrum. Shoot IR in, it vibrates the bonds. So you're doing this optical excitation of the material, and you get that spectrum. That's the fingerprint, and that's the frequencies where the material would absorb energy. So it's kind of interesting. So you can take mechanical properties, because at the large scale, you're getting the bulk modulus of the material. The mechanical properties, then the spectroscopy, optical spectroscopy, and the thermal properties of the heat capacity are all like linked together. Things you wouldn't think would have, like if I gave you the IR spectrum of something, and I said you can predict the DSC curve of it, you'd say, no, you're nuts. You can't do that. This says like all those things are the same thing, right? So it's kind of like a unifying. Anyway, so that's why people got kind of interested in this. Like if you start predicting, at least for perfect crystals, like what's going on, you know. in terms of the dynamic features of it. And it comes back to thermodynamics. So it's kind of like everything ties together in this, right? So density of states is like how the energy is distributed. And then and also you want to know what's the frequency of vibration at different size scales. Like I said, say you're at a large meter size scale, then the frequency of vibration is just like push it across the table. And then as you go to smaller size scale, you get a frequency. The material acts like a spring, like a bell, and it's the modulus of the material and the mass that determines the bell frequency. And if you go to very small sizes, then you're looking at the atomic stretching of the thing, right? So basically this dispersion relation is telling you how frequency is distributed versus size. So frequency is energy, so H nu would be energies. It's got how the energy is distributed at different size scales. So this is how the energy is distributed. So how many things are excited at different energies or different frequencies, and so how energy is distributed at different size scales. So that's called the dispersion relationship. So and the x-axis isn't size, it's 1 over size. It's 1 over size because, so why would it be 1 over size? So the reason it's 1 over size is that you have, so it's called the wave vector. So this brings you back to this idea of a Brillouin zone. Okay, so if I have my atoms here, and I'm gonna, if I have a very large wavelength, say transverse acoustic wave that's just coming in. So that means that this guy will go up, that guy goes up, this guy goes down, like, so it's kind of going through the material like that, that's fine. Then I make a smaller wave, finally I get to a wave that's like just the size of the atoms. So my wavelength by 2 equals the lattice space in this A. Like, so there's 2 size scales of wavelength we're going to put it on. So if I get larger, it's fine. If I get smaller, I reach a point where if I go smaller than that, so the motion is stuck, like it's the same motion, right? See, so it's the black things moving is the only thing that matters, and what I put into it is just exciting that motion. So you have a fixed vibrational wavelength that comes out. It's not the same as the wavelength that went in, right? The material is converting it to this, and there's a minimum wavelength that I can reach, right? In other words, because the atoms are spaced at a certain distance, that means that the effective wavelength of the sound wave that went in reaches a minimum. So if you take 1 over that, that's a maximum. So the wave vector is 1 over that, or 2 pi over the wavelength that went in. It's just K wave, or sometimes called Q. It's a wave vector that goes into the material. So instead of talking about size, you talk about 1 over size. It's like a Bragg. If you do diffraction, you use the Bragg's kind of inverse space that we talked about, Q, which is 2 pi over lambda sine of the angle. So the angle space that you look at in diffraction is actually 1 over size. So there's a Miller indices are all 1 over size. Right, so this is kind of like Miller indices, except it's got dynamics involved and statics. So anyway, so this is called a wave vector. Basically, you're talking about 1 over the wavelength of what you went in. Because you have a minimum here, you have a maximum there. So this cuts off at pi by a, which is the minimum size that you could, so 1 over the minimum size that you could excite the vibration in the material. Right. So you have this is called a Brillouin zone. So you have pi by a's the maximum number, and it can be plus and minus, and then 0 would be infinity. 0 would be the thing moves across the table, the bulk sample moves, right? And then if you get to smaller sizes, you have this linear part, and the slope of that linear part is square root of the modulus by the mass, like a bell. So that's like a bell ringing here, and then you gradually get to the smallest sizes, and you get to an atomic the cohesive energy density level of the thing. That's like where the atoms are put together. Right, so basically that's kind of the behavior. So in the Einstein model, there's none of this size scale dependence to anything. It's just like it's just one number here. It's flat. It's just got the number, because it's just Einstein is just one thing. So there's only one number from it. It doesn't have to do with this kind of size scale dependence to it. Right. So the Debye brings up this idea that no, there's some dependence to this. So to get this signed function, you go to this model. Okay, and this so basically you're going to say, let's see, somewhere here I have that done better. All right. Early. Sorry. I can get there. Not there. Here. All right. So you have, if you talk about the spring constant, the force is K times the spring constant, right? So in this case, you have, say you have three springs, you have the center atom, UN, then N minus one, N plus one. So you're going to have like the motion of that, K times UN. Then there's an opposing force from the other atom, which moves. So it's K times UN plus one. And the same thing for the previous atom. So it's UN minus one. So you end up with 2 UN minus UN plus one minus UN minus one. And then this is a balance between the motion, so the mass times acceleration, and then the spring constant. So spring constant times the position of the three atoms. So basically for this center atom, it's got a mass times acceleration force, and it's got a force due to the spring constant, and they have to balance out. Then you can solve that differential equation. The solution to that is this sine wave thing, basically. So you say the thing is going to follow a wave function, and there's this phase lag to it. So you have n is the index of the particle, a is a position, and q is the wave vector. This q is k, the wave vector that's plotted in the dispersion relationship. And then if you integrate this thing, so second integral gives minus cosine, first integral gives sine, and then you end up, or you have cosine here, so you end up with, you do that balancing out, you get the equation. So here you have mass, here you have spring constant. This thing becomes square root of the spring constant by the mass. And that gives you this dispersion relationship. So Einstein is just a flat number, and this model that includes collective motion, which is the basis of the Debye model, gives this dispersion relationship, which is like the standard one. This one's kind of useless. It's just one number. This is the standard one. So sine at small sizes can be expanded to one plus or it just expands to the argument. Somewhere it says that. But so at long wavelengths, so the sign of something, if you get small wavelengths or small, like close to zero, becomes just the argument. So you end up with QA, and then we got 2. So you have this prefactor, square root of 4 is 2, so it cancels. Then you just get the frequency as that. That means that if Q is a wave vector. So basically, the derivative, the slope of this thing is going to be the modulus when you get to large sizes. So you go bulk motion, 0. I mean, there's no frequency response. Like if it just moves across the table, it just moves. That's it. So it's 0. Then you go down, and then that's when this is small, so you get a linear, and then you get the modulus for the slope, modulus by the mass for the slope, and then it tails over. It follows this sign dependence, and the intercepts for k over n for here. See, this is plotted frequency over 4k over n square root. Right? So it goes to 1 on that, using that reduction. So anyway, so that's the first and the like the easiest part of and it might seem hard, but basically that's the easiest part of the Debye analysis, is giving this dispersion relationship that relates how the frequency is distributed with size. Like if you go to larger and smaller sizes, what's the frequency of the vibration for a collective motion, like the simplest possible collective motion, which is just glued together. That's where the linear thing is, but. So. Anyway, that's the simple part. The more difficult part of this is the integral to get the equation for heat capacity, right? Which is kind of like a little bit messy. Oh, all right. So this is a derivation. I have this linked on the web page. It's a derivation of this equation, which gives so that was for a transverse wave, right? So, but that was for an acoustic wave. But so if you want to do this for an optical and acoustic waves, it gets pretty messy. Like, I don't want to go through this. So basically, there's a web page that shows it, but the end equation of the analysis. So this is like you have an Na and a Cl, and they're of opposite charge, M1, M2. And the plus minus is if they move in the same direction or an opposite direction due to the stimulus. In other words, if it's an acoustic stimulus or an optical stimulus, right? So anyway, this thing goes through that. There's a link to it on the web page, but basically this is the answer to it. So the minus, if you choose the minus answer to this, the root of that, you end up with the acoustic, and if you choose the plus answer to the root, you get the optical. So that what happens is that the optical, when you get to zero wave vector or infinite size, the optical has a value, the acoustic goes to zero because this is frequency on the side, there's no frequency to a bulk motion, but there is in terms of optical, when you get to large size, there's a bulk polarization of the material. So it's all the NAs can go to one side and all the CLs can go to the other, and then the thing has, like, it's polarized. So there is a frequency response at zero for optical. For acoustic, there isn't, because it just moves across the table and stops there. So it's still the same stuff at the end. So basically, and you can see in those curves, like so these are just the acoustic modes. Let's see. Here, so here's an example. So your CL and the optical modes, when they get to zero, all have a value, and the acoustic modes all go to zero. Right? And then they have various forms because of the atomic structure of the material. So these are measured with something like Brillouin scattering or Raman scattering. Right? So these are like measured things, not from a theory. And these are also measured density of states from Brillouin scattering or from Raman scattering. So these things can be measured, or they can be also simulated. Like like density functional theory, you can do a program, it'll spit out density of states, dispersion relation, more or less. So basically you can get these either from simulation or from experimental measurements, not from heat capacity measurements, but from optical spectroscopy measurements. And then these can be integrated to get the heat capacity. So there's an interchange. You can measure the modulus, you can calculate the heat capacity. You can measure the spectrum and get the heat capacity. You can calculate the heat capacity from the Debye function or the Einstein function, and you can measure the heat capacity. Right. So there's like 4 ways to get at the same thing, same number, right? So anyway, let's see what else I got here. Anyway, so this derivation, so this is there's a couple of pretty good online derivations. Our book doesn't give a good derivation. I think there's a Kittle book, a physics book by a guy named Kittle, that's pretty tough to read. So there's a bunch of derivations of this. There isn't one. So I'm taking the Wikipedia derivation, but even on the Wikipedia page, there's 4 derivations of it. So it's not one. So basically, this derivation, the one I'm showing, is Einstein's original derivation of Debye's original derivation for the heat capacity, right? So, one thing that I have to say that I'm a little puzzled is that like, mostly people talk about it, it includes like a collective feature of the atoms, meaning that like you're going for this model, like this thing, the spring thing. So this one's impacted by the other two. It's not exactly clear. It's clear here, like that if you do that here, then you get that answer for the dispersion relationship. But for the heat capacity calculation, it's not exactly clear how that model fits in, except that the Einstein calculation is done in just for one thing, just for like just one calculation is done for that. The Debye calculation is done for like this. So it's done for a whole crystal. So he's including other atoms in the derivation. It's a 3D derivation. Einstein is 1D, this is 3D. Somehow that action gives you this coupling. So usually people show the coupling separate from the integral. So there's a lot of things that are a little bit loose end here, right? So I think it's important to figure out exactly. People talk about it like this isn't coupling, this is coupled interactions, right? So, but exactly how that comes out in the math is a little bit mysterious, somewhat. But that's the argument, that the difference, why he gets the right answers. Anyway, so he starts in 3D instead of like 1D. So he's got a 3D integral. So this is the distribution. This is the distribution of energy, which I got last time is this Bose-Einstein distribution, which is this is in the Einstein equation. In other words, this thing squared is part of the Einstein heat capacity term, right? This 1 over E or KT minus 1. I got this last time. Anyway, this is called the Bose-Einstein distribution. It's how energy is distributed. And there's how many of elements do you have that have this energy E? So, and basically the ones with the lower energy, is more of them. Is how this works. There's a plot in this Einstein thing here somewhere. This is slide 55. That's it. No, that's not it. I have a plot of that somewhere here. Nope. Anyway, somewhere I have a plot of that. Maybe it's below that. Nope. Where is that? 55. Let me see. 55. Sorry. I'm busy. Let's see. Um, so I guess this is a plot. So this is it MB. So you have the lower, let's see, what's this? I'm looking for against energy. Good. Average population. I guess it's something like this. Yeah, the lowest energy has the most, and that decays down. That's the idea of it. Yeah, so the lowest energy has the highest population, it decays down. High energy has fewer. Right, so we kind of got that same way that we went through the Einstein thing. This should be in the things here, but anyway, so that distribution going to plop in here. So Einstein uses his own distribution, yes. Then this is the energy. You want to find the average energy because you're going to take derivative of this with respect to temperature, gives you the heat capacity. It's trying to get the heat capacity. So to get that, you need the energy. So he integrates over all energy, uses Bose-Einstein distribution, plugs it in there. And he says it's for, so if you have a simple vibration, there's so in other words, it's a compressive, say you have a string of atoms like the picture I showed at first, we have n plus 1, n minus 1. There's only one like longitudinal, they just compress like an accordion, just like accordion going down. Then there's two, it's like X and Y. So there's 3 kinds of vibration it can have. So that's why he says each one is going to have a Bose-Einstein distribution. So there's 3 times that gives him NE. So he plugs that in here. So now he has this kind of more complicated integral. And then Einstein did this weird thing, like he thought it would be easier to solve this with just one parameter instead of three, XYZ. So he went from Cartesian coordinates to spherical coordinates, which complicates it a little bit, but basically the angle terms drop out. He just gets a prefactor from the angle terms and just gets one integral left out of this. It's a simpler integral. So when you do that, you get this, you have n squared. N is a number of atoms that are contributing to the excitation, to the vibration. Right. So the total number in the unit cell is capital N, and then N is the number. So you're going to integrate from 0 to 3 to the square root of capital N, because you're going X, Y, Z. So it's the cube root of it, and the total number gives you the number in X. Right. So anyway, if you convert that to spherical coordinates, you have these two integrals over angle, and those don't depend on n, so those drop out and just give you a prefactor of 3 pi over 2. Then you just have an integral over the last one, the dn, which is 0 to r, and r is the cube root of 6n by pi, which is like the number in a radial direction going out when you convert to spherical dimensions. And then the total number. So he says that his sphere, so if you had a cubic 1 unit cell, the crystal, and then you have a sphere that you substitute for it, the cubic unit cell is 1/8 of the sphere. That's an approximation that he uses. So that's what this 8 is here. Otherwise it's 4/3 pi r cubed. This is sphere volume, then 1/8 gives you the total number that you have for this n that you get r from. So basically, a little bit of hocus pocus math stuff here. If you, at least in this derivation, again, there's 6 derivations on the wiki page for this. And they're all slightly different, So anyway, so if you can accept that, then you can plug that into this equation and then use that the energy squared, so it's 3D. So he has this energy squared. So he has to square each of the axes, then kind of h nu, and nu is so h nu is hc over lambda. Let's see. Yeah. So if you convert nu to lambda, you end up with the speed of sound, cs by lambda. So he ends up with this cs by L as the unit cell parameter. So anyway, he gets the energy is like h nu is what he's using here by 2L. So this is kind of in this isn't his energy distribution like his sine wave energy distribution. This is just a linear. This is like he had this from the springy balls, end up with sine. So you end up with something that looks like that. So he's just talking about this part. So this is like the energy over H. Right, so he's only talking about this part where it's like linear, like the modulus part when he plugs in this. So I guess this might be where, actually this step might be where he's connecting back to the springy ball model. Like when he says the energy is this, that's coming from that. That's not the Einstein energy. This is the energy from this springy ball thing. So he's plugging in this expression into this thing. And then he's saying that n squared and is the same thing as n squared. Like his n squared equals this thing. Right? That's just going from Cartesian to spherical. So it allows him to get rid of that and just put in n squared. He's got that same prefactor here. This is energy squared, so he takes the square root, gets that thing, and then he's got the Bose-Einstein distribution here, and he plugs in his energy to that thing too. So he's got this kind of messy thing that he's left with, this integral 0 to r dn. I mean, Debye was a genius, so you kind of have to give him the credence of belief here. I mean, you can go through this step by step, but basically, Anyway, so then let's see, so then you'd substitute in this X to get rid of all the terms. You say X is HCSN2LKT, so you had HCSN2LKT, which is like, let's e to the X minus 1. Right? And then this thing is HCSN over L, 2L is X times K, I guess. So there's an X by K, or he just keeps that here. And then somehow this thing shifts around so that that integral becomes this integral. That's exactly how I did that. Oh. Anyway, convert the integrals to get to that integral, and you substitute in the you define the Debye temperature, which would be theta d, here's TD, as this kind of collective term, which is the argument for the integral. So you're going to integrate from TD by T. This is T by TD cubed. And then that's the Debye energy term. And then you take the derivative of that and get the heat capacity, which is this guy. So it's kind of the same thing, but the derivative with respect to T gives the heat capacity expression. All right, so anyway, so that's kind of, I think in the homework, kind of confusing because I'm already past this homework. The homework on the Einstein kind of wrote for due yesterday. No one turned it in. So I guess it's due Wednesday. And this is the homework for next whenever. Right. It'll clean up at Thanksgiving, I guess, but anyway, so you have to go through this derivation. You can look on the wiki page. Again, you can look on this page. There's a lot of people have this derivation. You know, this is this Libra text, which is usually pretty good. This is pretty good. And he's showing phonons. That's a transverse wave in a crystal. Usually these Libra texts are pretty good. And there's a bunch of books. There's our book, which our book isn't that great for this. And then there's a bunch of other books on the web page. They can let me just go books. I'm looking for a Kittle. So Kittle and Cromer is one. This Dove has the same thing in it. Both of these Dove and this Kittle. So anything with Kittle or Dove in it. And the Hill has it in it. So again, like if you look at these, you might get like, it's not as good as looking at the wiki page. This, that's it, I think. Anything with Kittle or Dove in it. There's 4 books there. All those are pretty good for this, but it's a lot of math, you know, so you might need to really spend some time looking at it. If you want to look at it, the wiki page is long, like it's pretty long if you go to that. Function. I think this is the Debye function. No, it's not the Debye function. It's the Debye model. Oh, yeah, this is the thing. So, I mean, this kind of defines the Brillouin zone, right? Like there's a shortest wavelength that you can accommodate, or longest wavelength you can accommodate, or shortest wavelength you can accommodate, or longest wave vector you can accommodate in a crystal. This shows that. I mean, it doesn't show it as a wave, it kind of shows it as V's, but so if you go to shorter wavelengths or higher wave vector, it just repeats that over again because atoms in the crystal convert it. Yeah, see another derivation, yet another, so it keeps going, it's like a bunch of derivations in here, so that's a the Dubai model. I think it's linked somewhere, but that's the thing that I kind of looked at, but there's anyway, so and that Libra text thing is pretty good too, if you want to look at it. What else? All right, so that's good. Yeah, so you can take the limits and find, you can get the Dulong Petit from it if you take the limits. So the exponential expansion goes to the linear at high t. This is a small number, so you can use that expansion, and you can plug that in, get a simplified form for the energy, and then take the derivative of that with t. So that energy becomes 3n kt, and derivative with t is just 3n k, which is the Dulong Petit 3r. CV over R is 3. So both Einstein and the Debye revert to this 3n to the 3r heat capacity thing. And then so let's see. So the density of states you get from the dispersion relationship. So, and that's a complicated process to do, right? So basically there's a simple case of doing that here. Like if you have a dispersion relationship, which would be the sine thing for the Debye, then how would you get the density of states? Like those two things are related to each other. As you can convert from dispersion relationship to density of states, and density of states the dispersion relation. I showed you let's see, this is 49. Someplace I showed that they were paired up, right? So they're looking at the same thing, just different aspects of the same thing. Here, yeah. So this is for cuprous chloride. Somehow these two things are tied together. In other words, you can calculate the density of states if you have the dispersion relationship. You calculate the dispersion relationship if you have the density of states. So this is measured by spectroscopy. So they're both measured by spectroscopy, basically. Or you can calculate both of these from a computer simulation. So if you want to, so that the only place I can find that where they actually do that conversion is just talking about basically the Einstein model. We have a single frequency. So so this just defines a term. So the wave vector is 2 pi over the wavelength, and the frequency, the angular frequency is the. So if you're relating frequency to k is what you want for a dispersion relationship. So that's the dispersion relationship they're saying, and that's basically the Einstein dispersion relationship. You just have one value of frequency. So it doesn't matter what. So they're just 1 to 1, right? So anyway, so to probe this, you use a so this is just a wave equation because e to the ix is cosine x and I sine x. This is kind of like electric magnetic field oscillating type thing. So this is like an electromagnetic wave equation, but basically e to the ix is a sine function. So if you say for this, so these aren't, there's no time component to these, right? It's just the relationship between frequency and wave vector. Like there's no time dependence to it, right? So if you look at so this thing, you can forget about the time dependence and just use e to the iqx for the wave, right? Without the time dependence. And then you say, like, if you have a box, so you're talking about like two atoms separate from each other. In the Einsteins, you have like the 0 and the position L. If it's a box, it's L. If it's two atoms, it's A, right? X will be A, but here it's L. So it's from 0, so that the motion of the atom has to be the same as 0 and L. And then if you plug in this wave to it, then when x is 0, that's 1, and when x is L, it's EI QL. So those two have to be equal, and as you can solve for the Q in terms of L, 2 pi over L. So, and then you can take this dispersion relationship. So frequency goes with K, so the Einstein, and take the, you can take the derivative of this to get this dq d2 pi L gives this expression. So if you say the density of states, let's see, how does this work? So the integral of the density of states, like how many have that frequency, is going to be like dn from this expression will tell you like how many have that frequency. N is how many. So dn is this differential density of states. So you can take that, get this expression. If you integrate that, you get GW is L by pi by d omega dq. If you take this, you can take the derivative of dq and you find out it's the frequency. You just plug in the frequency. Then you get a density of states. So it's starting with just a calculation of what density of states are, and it's using the dispersion relationship when you need to know this d omega dq. So the relationship between omega and the wave vector q is the dispersion relationship. So g omega is dependent on 1 over that. I guess that's basically the argument here. If you want to know the density of states, you need this derivative. And if you have that derivative, you get that from the dispersion relationship. So that's how they're related to each other, by an integral, by a derivative or an integral. If you want to integrate this thing, you can get that thing. When you take a derivative of that thing, you can get this thing. So that's the argument of this thing. This is one of the Libra text things, but it seemed pretty good. It's the only place I could actually find where anybody showed you how to go from density of states, go from dispersion relation to density of states, and the other way around too. And this is kind of the key equation. They're related by a derivative. Right. So anyway, so I think that's kind of important. Anyway, it's a question that came up in my mind, that if these things are the same thing, then how are they related to each other? And this equation basically tells you they're related by an integral or a differential. Anyway, it's kind of dense stuff. What else is in here? Temperature, we got that. The high temperature and the low temperature limit. All right, the low temperature is kind of easier because at low temperature, the X becomes large, and then this 1 drops out, then that cancels. Let's see, X becomes large, temperature. Cancel. This is bigger than that. So that just becomes X over e to the X dx. I guess that integral can be solved. I have that someplace, the solution to that integral. But anyway, it ends up just being the prefactor. Oh, when you plug in the 0 to infinity, I see. So when you solve that integral, somehow this becomes 1, this argument. And you just get the prefactor, the t by t d cubed at low temperature. So the signature is this cube temperature dependence at low temperature, and that's what's seen. So it's a perfect fit at low temperature. I don't think I have a plot that shows exactly, but I mean, this region is what people are interested in. So they, like in the paper this week, they do that t squared plot, right? T squared minus t or something plot that shows that dependence. Let's see, there's that guy. Must be tough on like 3 classes in a row for you guys. It's like pretty insane. Like, I don't know why they schedule it like that. It's pretty nutty. Like someone should like complain that it's too much. They have the whole week, like they could schedule it sometime, but anyway, this guy. So here, this is the divide dependent. So he's plotting, let's plot it here. Temperature. Oh, this is conductivity. And this is C by T. And this is T squared down here. So this would just be a linear T dependence for the Debye. Like this is the Debye one, this is the Einstein one. It's got the high heat capacity. And then so anyway, this is linear because linear in T squared because it's going to be T cubed. So like T cubed in a T squared plot's a line, right? And then this one isn't a line because it's following the that kind of exponential dependence in the Einstein equation. Plus, I mean, he's adding also in the electronic contribution, this gamma T term. But so anyway, yeah, that isn't very impressive, I guess. That's why I didn't have a plot of it. Maybe. Let's see. Well, temperature, high temperature. Oh, and this is just showing that. So you have this by temperature, which is usually theta E, and then theta E for the Einstein. So they're related to each other. I mean, well, they're related to each other. Basically, there's a factor that relates the two together. There's an expression, they have the same terms in them. They're just Einstein's lower than the Debye temperature. That's just showing the two temperature limits to the. So the Einstein ends up with this one over exponential term, e to the minus e kt to k. And this is just this cubic term. The low temperature, high temperature, they're both the same. Then the Einstein and Debye temperatures are related as 0.8. What else then here? This is copper metal. So you can see the Debye matches the copper metal curve at low temperature, and they both are kind of the same at high temperature. And this is kind of interesting. This comes up in the paper so there's 2 homeworks now, but the second homework, it talks about the different poly or allotropes, I guess, of carbon, right? So it's like buckyballs, graphite, and diamond have different heat capacities. All right, and then it asks about like if you raise the temperature to 1,000 degrees, the graphite heat capacity is larger than the let's see, the diamond becomes larger than the graphite at like 1,000 degrees or something. Anyway, that's in the homework this week, but it's just showing because the atoms have different. It's the strength of the bonds between the atoms that is deciding the dependence of the heat, and also the 3D arrangement decides on the kind of. So if you reduce these by the Debye temperature, the curves kind of fall on each other. That's another thing, but anyway, and that's a periodic table showing like stronger bonds have a higher Debye and Einstein temperature. The Debye temperature is given, and this gamma is the electronic contribution to heat capacity. So stronger bonds, higher Debye temperature, higher heat capacity, or lower heat capacity. So the stronger the bond, the lower the heat capacity. The higher the Debye temperature, the lower the heat capacity. The higher the Einstein temperature, the lower the heat capacity. Right, so it's kind of like inverse. And And then like basically this just comes out of that, like the idea that you can get the modulus from it just comes out of that linear part by the Debye dispersion relationship, and then at the low end you get the basically the modulus K is going to be like the modulus. So stress strain K. So if you know the Debye temperature, you can predict the modulus, like because of the this Km is going to be decided by the Debye temperature. So in other words, from the Debye temperature, H nu over K, so nu is the Debye frequency, and this is the frequency. So if you know the Debye frequency, you can plug it in here. If you know the mass of an atom, you can get the modulus for copper from that Debye temperature, which is measured from a DSC curve for the heat capacity as a function of temperature. Right, so that's kind of the link between. So you measure the curve. You fit this with the Debye function, you get theta d. And then you take theta d, you can calculate the frequency, plug the frequency into this for the linear part of that curve. And if you know the mass, you can get the modulus. Or backwards, if you know the modulus, you can plug it in here. If you know the mass, you can get the frequency. You can calculate theta d, plug it into the Debye, and then you can get that curve. So it works forward and backward. The modulus will give you the heat capacity will be the modulus, right, for the acoustic modes. So this is showing like doing that for a bunch of things, right? In other words, different metals. It has to be a crystal. This is the Debye. This is the Debye calculated from the modulus. It's the same number. Right? In this paper. So anyway, yeah, so the elastic and the heat, and then from the heat capacity measurement, the numbers are the same. With the same number for this Debye temperature. So when I put there, so this is just how you, so all these are from CV, right? So basically, you're going to measure CP. So basically, somehow if you convert that theoretical CV to CP, so this is, I'll talk about that next time. This uses this this Gruson parameter to do it. And Gruson is a guy who wrote the he's one of the authors for the papers, this number 12 homework. Like this is a Gruson. Oh no, this week, right? Sorry. Gruson is oh, that's Gruner. Sorry. Gruner is the other guy for electron. It's also gamma. There's two different gammas, sorry. Anyway, so why don't we put there, like next time I'll pick up on the CVCP thing, and there's like a whole nother couple lectures on this, I think, about heat capacity, like polymer heat capacity, and some other stuff. Electronic heat capacity, magnetic heat capacity. So there's like a whole series of heat capacity things for materials, So anyway, so I'll do that next time. So hopefully the homeworks, anyway, there's 2 homeworks now that are outstanding. So you can do 12 now, like with what I did. So it's basically like do that Debye derivation. Optical acoustic phonons. How's it related to hardness, heat capacity, square root of stiffness, and Wonderlic. This is the thing about graphite and diamond. And anyway, so this equation 3 and 2 are the Debye equation. So that says like derive the Debye equation, which is what I did, like the wiki page derivation. And then how does he get the Debye temperature? So he gets it from a modulus thing. So anyway, that's it for that. Yeah.